Hello, and welcome to this video, which is part of the series covering basics of linear algebra for quantum mechanics. In this video, we will continue our conversation of vectors and we will look into what does inner product means in the Euclidean spaces. In the Euclidean space, the inner product will help us to find the length, distance, and the orthogonality of the vectors. To start with, multiplying norms with the cosine similarity is done on the basis of the vectors and the angle between them. Taking the cosine of that angle will help you calculate the cosine similarity. Example, if a vector are perpendicular to each other, the cosine of 90 degree will lead to an output of 0. It is important to understand that all the vectors that we are using here as an example has an L2 norm which is equal to 1. That means the vectors are normalized. If the vectors are completely opposite to each other, then the cosine of the angle, which is 180 degree in this case, turns out to be -1, which means that the vector have no relation with each other, no overlapping relationship with each other. They are diametrically opposite. Similarly, if you have an angle between 0 to 180 degree, there is certain overlapping relationship that can be calculated by the cosine of angle theta between them, as you can see in the third example. How to calculate the inner product of two vectors? Given two vectors A and B, calculate the complex conjugate of the first vector, which in this case A, denoted by A bar. How to calculate the complex conjugate is defined in the previous video, so I do recommend to watch those videos in the series. Then the complex conjugate of the first vector is multiplied element by element with the second vector, and all those multiplication is summed over. Now it is important to note that if you multiply the same vector with itself, it will be returned an scalar value, which is the magnitude, which is the square of the magnitude. Now it is important to understand that norm is directly related to inner product, and the norm we have seen in the previous video. For understanding purposes, in this video, the norm is L1 norm, which is normalized in this case. Orthogonality that we have used as a term at the very beginning of this video has to deal with showing the overlap among the vectors. So, two vectors are orthogonal if their inner product is 0. It means that the orthogonal vectors are perpendicular to each other. That's when the cosine of angle between the two vectors results in 0. Which can be interpreted as no relation between the vector. Another term that you may encounter is orthonormal vectors, which means orthogonal vectors with norm 1. So it is important to keep this distinction into consideration. How do we calculate the vectors which are described by orthogonal vectors? So two orthogonal vectors, for example A and B. You can calculate third vector C, which is in the complex space, which can be multiple of A and B, as can be seen in the example here. And it is helped by calculating the cosine between the vector c and what it holds in respect to vector a and b, and that will give you in terms the space position of c with respect to two orthogonal vectors a and b. These concepts help us to extend further into what is called as base vectors. So given a complex vector space, base represents the set of vectors to construct every element from the given space vectors. So for example, if you see here, you can calculate a base vector which is part of a complex space, another vector c which belongs to this complex space, which is combination of the dimensions and the inclination of vector c with respect to the orthogonal vectors a and b, which are in the same complex space. Saying this mathematically is that given a complex vector space, you can construct a vector v belonging to the space from base vectors b belonging to some vector space b which is part of the complex vector space, and c which represents the complex space in the wider complex space that we are talking about. And you calculate the product and summation of the product of the vectors b and c over the number of elements it has. So this is how the vectors are calculated in terms of the orthogonal vectors, and this is how the concept of base helps to construct new vectors. I'll stop here and I'll hope to see you in the next video. Thank you very much.